give an overview of the hardware virtualization now that we will talk in more detail in a later video. So what happens really is we provide still two levels, well, really 4 levels, but 2 levels that we use of CPL0 and CPL3. However, this is packaged up into a guest mode. So really we're in this situation where we've got the guest kernel that can be running in CPL0 and the rest of the code can be running in CPL3, and you can arrange it so that traps from CPL3 go into CPL0 and so on. And this then is operating on, this has privileged registers. But this is all itself inside a larger actual hardware. And this hardware has a host mode. And this host mode, in some sense, it's a higher privilege level outside of the CPL0. So we could have multiple guests, each with their own CPL0 and CPL3. And then there's a way to go in and out of this host mode into guest mode. So you can, for instance, do a VM run instruction, and that'll take you in to this mode. And then there are some various operations that can happen here that will take you back out to the host mode. So that is the this addition now of this host mode on top of this is what allows the virtualization. Now, of course, these guest modes don't have full access to the entire hardware because they don't themselves have access to the VM run. So the VM run instructions is intended just for doing virtualizations so that we can virtualize the whole rest of the x86 architecture, but not the VM run itself. And so this is one of the additions that was made to the x86 architecture to allow hardware virtualization. And in the paper we're looking at, it talked about early versions of hardware, and that was what they were talking about, so early version of this. The second change that was made to the architecture, the x86 architecture, was extended page tables. So if you'll remember, we have the guest virtual address, and then we have a guest physical address, and then finally we have a host physical address. And again, we looked at the fact that particular pages map in various ways. This was a guest page table, and this was a VMM mapping. And we talked about the fact that there was no way for us to have these two levels. We had to actually either have software that was doing this or hardware with having a single page table that combined the effects of both of these. Well, extended page tables actually say, fine, go ahead and have in your guest page table your CR3 register, and then have a separate extended page table. And this extended page table exists in conjunction with the guest page table. So that what the hardware will do is it will take a virtual address, it will take the CR3 page table, and will convert from a guest virtual address to a guest physical address. And then it will do an additional level of translation using an extended page table to convert from the guest physical address to the host physical address. So that is done by the hardware, and that way we don't need any shadow page tables, right? The guest OS can just make changes to its page table, and then the VMM has its own separate mapping from here to here, and then both of those will be applied on any memory access. What's better, doing the hardware or software virtualization? Well, one advantage of the software virtualization, so this dynamic binary translation, is that we can replace most traps just with callouts. So traps are expensive on hardware, and so by replacing them just with function calls, that can be cheaper and faster. The emulation speed, so the binary translator can generate some purpose-built emulation code, which can help. And sometimes the binary translation can even just inline callouts. A good example was the clear interrupts, where it just needs to replace the clear interrupt instruction with an instruction that changes a particular memory address. Hardware virtualization advantages. The translated code requires more instructions. So if we just use the existing code, that's simpler and easier. Precise exceptions. On binary translation, it's extra work needed to exactly get the correct state at the time an exception occurs. And for system calls, we don't have to have any VMM intervention. That is, we can just go ahead on a system call and have a trap occur, and that'll go directly from the CPL3 in the guest mode to the CPL0 in the guest mode. We can execute the kernel instruction and so on, as opposed to trying to get the VMM involved in that. The EPT is faster if there are a lot of changes to the page table. So if the guest operating system is changing this page table fairly often, then hardware is going to be quicker. However, if the page table is relatively stable, then when we've created a shadow page table, we just have a one level indirection to find a host BA from a guest VA. And so that means we have one page table to go through instead of two page tables, so that's quicker, fewer memory accesses. And also VMware really, with their binary translation, introduced this ability of virtualization on an architecture that was thought to be not virtualizable. That then went ahead and prompted Intel and AMD to go to change their hardwares. So that prompted Intel and AMD to change their hardware. And as you saw in the paper, in some cases the hardware is faster, in some cases the hardware was slower. There have been changes that have been made over the years since then to make that hardware, the virtualization, be faster. So that hardware virtualization is really what's used most of the time these days. VMMs are very common these days. The binary translation technology is difficult to build and do right. It's much simpler to base your VMM on a hardware virtualization as well. By the way, the I/O devices, so this is also newer, and they added something called I/O MMU. So that basically when an I/O device wants to communicate with memory, instead of doing direct memory access to physical addresses, it can actually do direct memory access to virtual addresses. So that allows a guest operating system to provide a virtual address to an I/O device and have that I/O device go through the same virtual address translation that the guest OS would go through. So that allows a guest kernel to talk directly to I/O and set up I/O reads and writes using guest virtual addresses. And that, again, doesn't require having to go back into host mode.